So I can't really see anyone in the audience, but whose first Star Trek is this? Like applaud. Awesome. I'm going to applaud too, my first Star Trek. So this is cool. I've never presented on an IMAX screen before. This is awesome. Hey! Oh, wait, that's my bad side. Yeah. Please make sure that's in the recording. So I already posted some information to the Discord and the little forums thing they set up. If you have any questions after this, feel free to ask me there. I also have contact information that we'll put up on the site, but it's really easy to get a hold of me. And I would love to chat with you, especially about this topic. Give another minute or two. I'm also going to preface that this is the first time I've done this particular talk, and it's always fun doing talks for the first time because you either have way too much material or you don't have enough material, and I'm not sure which is which. We'll find out together. But actually, I'm really hoping that questions from you all, either live or afterwards in Discord, help me kind of build out this material a little bit more. So if you have specific questions, I probably don't know the answers to them off the top of my head, but it's stuff I can go back and research and try to make this material better, because I think this is a fun topic. And obviously you do too, because you're here and not in one of the other half a dozen much better topics, by the way, than, now I understand those were probably full. You came here. It's all right. All right, 3:30. I'm going to go ahead and get started. Make sure we're all in the right place. Hello to everyone in the satellite room. Sorry you couldn't be here. We do have seats here, satellite people, if you want to come sit up front. If you're in the right place, let's build a simple web server from scratch. I want to talk about the idea for this talk. A long time ago, I used to be a college boy. And my college time was between 2002 and 2006. I went to Old Dominion University in Norfolk, Virginia, and I had classes in this building. I had one class in this building. This was the computer sciences building, which, funny enough, only ever had one computer science class in it. All the other computer science classes were in the Delaric buildings on the other side of campus that they were tearing down. They didn't love computer science. But we had one class in this building, and it was CS. I took 231 because I wasn't special or going for graduate classes, but there was also a CS 531 version that was about web server design. And if you ever have a beer with me, we're sitting around, we're just chit-chatting, I will go on record saying I hated college. I hated computer science education. I don't think I retained anything from it. But if I had to pick a single class that I loved in my computer science time at Old Dominion, it would have been this class, Web Server Design. And thankfully, I got this description from the current iteration of it. They're still doing it. And I'm glad they are, because I learned more in this class than I think I did in any of my other computer science classes. And the general idea was we, as technologists, kind of take for granted a lot of the underlying systems that we use day to day. Assuming most of you out here, probably a web developer in some way, shape, or form, or you talk to web services, or you just surf the internet every day. All right, if you're not that person, you're still on mainframe, awesome. But most of us probably use a web server in some way, shape, or form multiple times. If you have reception in here, your phone's probably talking to a web server right now, just selling all your privacy away. We rely a lot on these servers, but do we actually understand how they work underneath the scenes? And that's kind of what I wanted to approach here, was this class was designed to teach us how a web server works fundamentally and really make you grateful that technology works at all. Because you'll find out, and you'll actually see through some of the demos I do, it's amazing any of this stuff works. And you probably know that as a developer. It's amazing anything works ever. So, hi everyone, I'm Kevin. If we've never had the pleasure of meeting before, I am a Microsoft MVP. I focus a lot in the .NET space, specifically on ASP.NET Core, Microsoft Azure, and just web solutions. If you ever want to talk to me afterwards, I have some places on the internet I exist. I really should take off the Mastodon link. Anyone on Mastodon? 2 people? Cool. All right, 4. I saw 2 more hands. Excellent. You know, that was a cool time when we were all on Mastodon for a week. And then there was that one week we did Blue Sky. And then anyone do, I know, I'm just killing time. What was the thing last week? Not Clubhouse, Air Chat. Anyone do Air Chat? And some people are like, what the heck was Air Chat? Exactly. It was awesome for a day. Let's talk about client servers. So all those things I just talked about use web servers underneath the scenes. That's how you call back. You've seen this sort of illustration before. How does a simple web request and response work? You have a client and you have a server. Your client goes off and makes a request to the server. The server turns on it and spits back a response. The context you're used to it is usually, I'm making a GET request to a certain resource. I'm making a POST request to a resource, put, patch, delete, whatever. And the server is doing some churning. Or I'm opening up a WebSocket, and the WebSocket is going to do some work. There's a lot more happening underneath the scenes, though. So let's look at just a request. What's the formal definition of a request in an HTTP pipeline? Now, I'm not going to read it, but you could read it. This is from RFC 7230, which dictates how HTTP 1 works. What is a request? A request is a message sent to the server that has some information in it. And we have a response, which is also in 7230, that specifies that when we get a request from a server, we send back a response that has a certain format to it. And there's RFCs sections that dictate what the payload of that response should be. Now, I'm going to use the term a couple times, RFC. And if you don't know what that term is, what an RFC is, let's talk about that. It really stands for Request for Comments. And this goes for pretty much anything that we do in computing or in development and systems design. There's probably a RFC that goes along with it, meaning a working group or just a group of entitled, oh, no, I shouldn't say that, just a group of people much smarter than me get together and they dictate, this is the way that the world should work. And they all argue amongst each other. They build some prototypes. They go out to partners and say, this is what we think you should do. They go and do it, and they all come back and they argue. And it can take several years for an RFC to eventually get approved. The RFC that we care about for today's talk specifically are 7230 and 7231. These are the 2 main ones that kind of dictate how the web has worked for the past 30 or so years, because this talks about the client-to-server relationship, what the messages look like, how the messages should be responded back to. Now, the big question I got when I submitted this talk, and I was chatting with some other folks about it, it's like, well, Kevin, are you going to support HTTP 2 or HTTP 3? And the answer is, I don't have enough time to go into detail about either of those. They're very complicated. But they each have their own corresponding RFC. So there's RFC 7540 and 9114 for HTTP 3. If you want to go read these, you can just go look them up now. And it'll dictate everything that the society of our peers decided this is how HTTP 2 should work and how HTTP 3 should work. Now, there's an interesting thing about RFCs that we'll call back to a little bit later, in that they have some language in them. And I love RFC language because they use words like, you must do something, or no, you should do something, Or we recommend you do something, and a recommendation doesn't mean you should or shouldn't do it. It's just, we recommend you should do it. Or optional. And what this really means is that everything that they're putting into an RFC, for the most part, doesn't really matter. When I was taking the computer science for, 451, whatever it was, we learned very early in our discovery of implementing an RFC, we were told to test everything against Apache and try to do what Apache does. And we learned that Apache didn't follow the RFC. The RFC would say, well, you must do this, you must do that. But Apache wouldn't do this or do that. And we learned, okay, this is all optional for the most part. What's really cool about the terminology for RFCs is that there's an RFC for reading RFCs. So RFC 2119 will teach you how to interpret an RFC. Now this is the RFC for reading RFCs. Yep, 2119. And I only put a fraction of it. But these things get really long. In my GitHub for this particular talk, I have whichever RFC for messages. It's 109 pages long when you spit it out to PDF. I mean, these things have a lot of detail in them, and they're super useful, but they're a lot for one human to grok. And you're supposed to read multiple of them to figure out the bigger picture of how different systems are supposed to work. But it really comes back to the lesson I was talking about a minute ago. Not all existing implementations obey the RFC. I kid you not. I was working on the demo for this, and the demo is simple. I have a HTTP request that comes into my server, and it spits out files on the disk. Super insecure. You should never use my code in production, regardless. And it was working great in Edge and Chrome and Firefox, and I like, oh, let's open this in Postman to see what Postman spits out, because I wanted to show it as part of the demo. And I would run the code, or I would go to the URL, and Postman would say, malformed response, this is bad. I'm like, what are you saying it's malformed? Like, it's working fine in all the browsers. Turns out it was malformed, but the browser just didn't obey the RFC, and it was rendering my stuff anyway. So to an extent, our peers who have built existing servers and more or less clients, they know that we suck. And we're not going to do things properly. We're going to introduce bugs all day long. And they just figure it out for us. So everything magically works. Again, it's amazing that anything we do works. Let's get into a little bit more of the nitty-gritty. Let's go back to the client-server aspect of our application. So we have our client and we have our server. And everything fundamentally starts with a socket. So what's a socket? A socket is just a connection between our client and our server. We can have multiple requests coming through this one socket, but it's all bytes. So our client connects to the server, and there's an initial request sent in by the client. It's going to come in as bytes. Now, who can tell me what that says? Yeah, no one, exactly. So, you know how I know what that says? Because I put in ChatGPT. And it's spat it out for me pretty quickly. That just says get/HTTP1, which is the basic request that you send to any web server out there. Now, our web server basically has to take all those bytes and all the bytes that follow, and there's more and more bytes depending on how big the request is, and needs to turn that into some sort of message that we can parse and we can do something against. Then for our response, when we're eventually done reading the request, we can go do the work, figure out what the request wanted, create a response. Reusing that same socket, we can send what should be HTTP1, 200 OK. We have to turn that back into bytes, and those bytes go across the socket. Now, you probably never have to worry about this because the web server you're using, the framework that you're using, does all this for you. So this is the great part about standing on the shoulders of giants. They've taken care of all this part. Let's break down a request into some of its fundamentals. This is the base request you get in Edge, or really any version of Chromium, when you just open the browser and type in a domain. There's a lot of parts to this, but this is, again, going back to the RFC spec, in a very definable format. The RFC says the message format for a request will have a start line. It will then have a series of headers. Those headers are delimited by a carriage return line feed, specifically a carriage return line feed. And then when we're done with headers, there's an additional carriage return line feed, and I can have an optional message body. So if this is a post request or a put request, something other than a GET, I can send a message body, and there's other junk that comes along. And depending if it's a GET request versus one of the other method types, there's different ways that I can determine whether or not this message is done. Well, let's start at the top. The top is the start line, and the start line is simple. It's 3 octets. It's my verb, get, post, put, delete, patch, options, head, 15 more. What path am I looking for? Which resource am I looking for? And then finally, what HTTP version is it expecting to communicate on? I can take these, and I can go off, and I can go do what I need to do. Everything else is kind of sort of optional in the grand scheme of things. But most importantly, and that's why I spat it out, you need to have a carriage return after every line. There was a discussion kind of leading up to this is, well, is it new line if you're on Windows, or carriage return, whatever, if you're on Linux? How do you know which line ending you use? Specifically says carriage return line feed to just make sure across the board you're doing it the same way. There's a standard to it. After that first line, that start line, you have to define your headers. And again, if you're doing web development, you already know what a header is to an extent. We have to define our headers, and headers are all the other crud that comes along with our request. It turns out, as browsers and servers have tried to become more secure, more privacy focused, they've added more and more headers. I do work for a company right now where we scrape data from websites, and we have to pretend we look like people that we really aren't. We do. It's not like black hat stuff, but we try to do some non-natural things with web requests. We spend a lot of time in headers to make headers look like they're coming from official means and not our web scraper in the back end. So we spend a lot of time in headers. But all these are optional. All these also basically build your browser thumbprint. So if you care about privacy or anything like that, if you've spent any time researching it, you know, even if you're in private or you take your laptop to the other side of the world, Google and all of them can still figure out who you are just by the makeup of this stuff and by the makeup of your browser, the hardware that you're running. So it turns out you're not safe at all. I digress. What headers are required, though, if we're going in and we're creating this request? What do we actually need to handle? Well, the RFC says one thing and then does another, which, you know, it's not uncommon. The RFC says you have to have a host header, which makes sense. Here's the host that I'm trying to talk to, localhost, google.com, your domain. And it says a client must send a host header field. We talked about terminology. If I must do it, I must do it. But then, the same document down the line, there is, third line down, 0 or more headers in the message. I'm like, well, if I must have a host header, but there's 0 or more headers, then is the host really required? Like, I don't know. Turns out, if you forget the host header, it's still going to work. And then at the very end, you close up the message with either a message body, where you're defining a content length, so it knows how much data to look for, or you have a double carriage return line feed. If we look at this in raw bytes, this is what the end of my message looks like. 1310, 1310. Carriage return line feed, carriage return line feed. I said before, web servers and clients are really forgiving against malformed messages. My response that I was testing in Postman earlier was missing literally, let's see, this was request, it was missing the 4 or 5 bytes before the end of the message. And the client was just able to figure it out. It's like, no, Kevin, we understand what you mean. And we're going to talk a little bit more about the other headers in a moment, but every other header that you get naturally is optional. You don't have to do anything with it. You can just ignore it. When you send back a response, there's an equally long section in the RFC about how a response should be formatted. Most importantly, it's the status line. And the status line is going to be what we all probably know. I'm responding in HTTP 1.1. I'm returning a 200 status code. And you all out there know your status codes, right? Yep. Yeah. Who doesn't know their status codes? See, no one's going to admit it. Your 200s mean everything's good to go. Your 300s mean we need the browser to do something. 400s mean I screwed up as the client. And 500s means you messed up as the server. That's the easiest way to describe it. The status code, 200, is usually followed by the status description. Turns out the status description is completely optional. I could say 200 bad request, and that's okay in the RFC. But the client is never going to read the bad request, or if it does, it's not going to do anything with it. So if I say 200 bad request, it just knows, it was 200, it was fine. Good to go. You could say 404 okay, which I should totally write a web server that does that just to mess with people. Only on like April Fool's Day, right? So that's the important, the status line. Everything else is actually, for the most part, completely optional. We're going to come back and we're going to talk to everything else. What I didn't put slides in here for is how do you know that the message has ended as a client? And in this case, we can't use a double carriage return line feed because we're sending back a payload body. And the payload body could be a couple bytes. It could be hundreds or thousands of bytes long, which there's no way it's going to sit there and continuously look for a double carriage return line feed. Or my data might consist of a carriage return line feed or double. So what a request does is we define a content length. And we tell the client, I'm going to send you a payload after all my headers. You're looking for exactly 51 bytes worth of data. After 51 bytes worth of data, you can stop looking. You should have the entire payload. And that's what most clients will do. They'll sit there and they'll count all the different bytes. And once they have the data that they're looking for, they're done. Although, there have been times where you could say one number but send something else, and it just magically works all in the end. All right, let's do a demo. Let's show some code. So I have a demo that I've written in C#. If you are not a C# person, I'm sorry. It's like the greatest language in the whole entire world. Yes. Yes. Go Team C#. I am planning on doing versions of this talk in other languages because all your language really needs is a socket provider, which most modern languages do anyway. Except JavaScript, they have to go to C++ to get their socket provider. But, You know, let's not make this political, everyone. All right, so I'm going to show my bare bones, super basic, oh, that's big code. A very bare bones basic web server that I've written in .NET 8. And my goal was not to use anything in the framework that would do a lot of the heavy lifting for me. I wanted to try to do some stuff by hand. But I'm going to be perfectly honest. I really don't want to convert bytes to strings by hand. So I let the framework do that for me. Now, if you don't do .NET, this isn't actually the code that does anything. I have this worker that sits in the background, and it's going to open a socket, and that socket is just going to listen for connections. And every time a connection comes in, it's going to read from the socket until it needs to stop. It's going to parse the request, and it's going to send back a response. Let's just show this in action first. So I'm going to run this application. I'm going to open a browser, and we'll go to localhost 4321, which is what I'm using. And this is going to go load up an Astro site I generated, just a static page. But this is on my file system. And it's also serving up behind the scenes all the various junk that comes along with it. So let me refresh. Let me zoom in. We see, all right, there's localhost, there's my CSS. That's just browser BS, and then a favicon. Let's go ahead and set a breakpoint. And let's kind of walk through, not that one. Let's walk through a request coming in. So I'm going to say accept. I'm going to hit refresh on my screen. I hit a breakpoint. The socket has said, I have a connection coming in. Are you ready to accept the connection? I am. So we'll go accept it. Oops. And I just totally went through the code I wanted to show you. I just totally went through the code I wanted to show you. Oh, never mind. All right, so it's hit F5. So now I'm actually wanting to pull the message from the socket. And this used to be really cumbersome to do when I was a senior in college. And I was trying to do this in C++ because I had to read every byte. I had to do the conversion to a character array or a string. And then you're looking for special conditions. Oops. Please heed my warning. This is not efficient at all. If you're sitting out there going, Kevin, you should have did this, and you should have done that. I know. I'm trying to make this readable. And also, I'm trying to make it work. Like, that was the first part that was super important. It doesn't matter how fast your code is. If it doesn't work, it's useless. What we do is on the socket, we have a buffer of bytes. And I'm going to go to the socket, and I'm going to ask it to fill up my buffer. And then I'm going to take that buffer. I'm going to do some processing on it, go back, give more bytes, so on, so on. If memory is not a concern, which most Windows users it's not, you just take as much memory as possible. I could have a super big buffer and just get the entire message in one go. But I'm trying to be a little bit conservative here. I'm only getting a couple of bytes at a time, and I'm clearing the buffer. Turns out, I found a bug when I was testing this earlier where I forgot to clear the buffer, and I had all these extra bytes at the end of my message. And it turns out the client worked, my server worked just fine accidentally. But it caused me a problem with something else. All right, so let's go receive some bytes. I'm getting more than 0 bytes coming in. I'm basically generating a string as I go. And I'm showing you my work in progress, which we'll zoom in down here at the bottom. And this is getting my favicon. So you see, I got the request, the start string. I want to get favicon, HTTP 1.1, and then host. It didn't get the rest of it. So we have to go through the code one more time. So let's hit. I should really set breakpoints if I do that. So here. All right. I'm going to refresh this. I'm going to start again. Okay, so as my message builds, we can see right here, it's a different request. But it's now saying, all right, connection keep alive, which we'll talk about. We go through this a couple times. And I'm also doing a test in here for content length. I'm only doing a GET request, so it's not a big deal. But if I was doing a POST request or something that would have a message body, I need to know what the content length is as soon as possible. because when I know the content length, I know how much of a body I'm supposed to be receiving afterwards. Is it 10 bytes worth of data, or is it a regular JSON file that's a couple hundred meg? I don't know. So we do this test over and over again. And if we don't have content length, or something else happens, we're just looking for the end of our message. Do we have a double carriage return? Now I'm going to skip ahead just a bit to right here. Remove some breakpoints, get into my request. So my request is looking like this. So let's go ahead and show you the whole message body. There's a lot in here. So I'm asking for my default route, just slash. There's some security stuff in here. There's some cookies because it's localhost. And there's no message body. Now, how do I process this? Now, we know from the RFC that the first line is the start line. So I can go through and pull out the start line and divide it into its 3 octets, the method, the path, and the protocol. So method, path, and protocol, which should come out. And of course, the to-do, like all good developers have, I'm going to fix the issues later, which will mean never. I know that I'm doing a GIT request. Of course, you can't see that. GIT request to slash and HTTP 1.1. Now I have some code that goes through and it parses all the different headers. So if we go look at our headers, there's 16 of them, the keys and the values. Now I don't have a body, so I'm going to get out of that. And I'm going to take my request, I'm going to send it out to generate a response. And we know this is a GET request, so we'll shoot over to, which I just skipped over. All right. Now this is a different, it's a different request, but the first thing I do is I look at that slash. Now I can't translate a slash to anything on the file system, so I need to figure out what my default document is. If you've worked in any web server before, you know what default documents are. Do I want index.htm, index.html? Do I want X? Do I want Y? You can specify anything. So that's what we do. I have a special request in here for hello world. I'm doing my own handling. That returns some HTML. And that was just demo code that I accidentally left in production. But then I take this path and I go onto my file system to see, does the path astro index blah, blah, blah exist on my disk inside of my client path? And turns out it does. So it's going to read all that data in, figure out what extension it is, because we want to return the right content type. We want to be a good response. And I only support 3 types. So we spit out CSS, and we set up our basic response. And this is my object. It's a 200 OK. My request object, the body of the response, which if we go look at this, it's all the data in that CSS file. And then content type is text CSS. And then I have my last method, which spits out the response, which starts with the protocol and then the status code. Notice I'm not spitting out the description because I don't need to, and I just forgot to put the status in there. In the response, I need to tell it what content type I'm returning. I actually don't need it to. Browsers are smart. They'll figure most stuff out automatically. It's just nice of me to say I'm returning CSS. I have had times before, maybe you have with certain endpoints, it returns, say, JSON, but it's not content type JSON. Maybe it's just content type plain. So your browser doesn't format it correctly, or your browser doesn't process it correctly. So be nice, tell it what content type you're expecting. And then we have to tell it the content length. And this is a bug I fixed, where my content length is essentially the length of the body text plus 4 characters. And it's 4 characters And, comments don't lie, right? There we go. It's a comment. It doesn't matter. 4 characters because carriage return line feed, carriage return line feed. Now, my original bug was I only put 1 in there. I'm like, oh, we have 1 line feed. No, we have 4. All right, so I'm going to spit out the content type. We'll go down. We'll spit out the body, and then final carriage return. Now, we're going to put all this into a buffer, and we're going to send everything back in bursts to the receiving socket. Oops. And I accidentally shut down the browser. As you do during demos. Okay, so this is all running great. I'm delivering stuff to my browser. I can show you the same thing inside of Postman, and I'll zoom in the best I can. So if I just hit send, I'm going to disable these breakpoints. So I hit request. This spat back out the body for my Astro site. And we can see the 2 headers that I sent and the content length. And that's cool. This actually works really well. Another cool thing you can do, and I'm going to remove all the breakpoints. Yep. So while this is running, I'm going to put 2 windows side by side. So that's my web server. And every time I make a request, it spits out what the request looks like. But I have another browser over here, or another terminal, where I'm going to do a load test on it. So what happens, Kevin, when you throw 10 connections at a time over 500 connections? It turns out it's really super efficient. This is a single-threaded web server that can handle 500 super basic HTTP requests in a couple nanoseconds, or microseconds, whatever seconds, or milliseconds. So yeah, that all works super well. And I thought, just for fun, let's move this up to, how about 100 concurrent? I want to test, I'm testing gzip, which actually doesn't work on this server. So yeah, it's just regular stuff. I broke something. Connection reset by peer. So I did something to crash my server. I don't know what, but I crashed it. See, that's why you only do that sort of demo during the live, because if you don't, you'll never know that it broke. All right, let's jump back over to slides for a minute. Where we are. All right. We're doing well. Let's talk about the accept header. The accept header is one of the places where you can start to get creative. When a web server sends you a message, it's going to basically give you suggestions on how you should return a response. Let's say, and this is really a big deal today, but this was a big deal a couple years ago. And I think as we add more and more formats, this is going to become a bigger deal. Accept tells the server what formats and what order format a client would like to receive something. So if you make a request to a server and you say, I accept HTML, I also accept XHTML plus XML, or worst case, just give me XML. The server can go through and say, well, that request doesn't return as HTML. I'm going to give you XML instead. And it'll do that. For images, so this browser is saying, I forgot I had a zoomed in version of that. I'm sorry. So we accept HTML or HTML plus XML, which used to be a really cool thing like 15 years ago. Not so much anymore. Or I accept XML. But it has a Q value, and the Q value is like, look, worst case scenario, use XML. Like, I accept it, I just don't like it. That's what the Q means. For images, the image will say, well, I want AVIF, I want WebP, I want APNG. This is the order I like. Now, this isn't saying this is my order of priority because there's no Q value. Oh, yes, yes, there is, but not for these. It's just saying, give me any of these three if you can accept it. So technically, if you get a request for an image and they ask for a bitmap, and you say, well, I only have PNG. You can send back the PNG and it should all be perfectly okay. Because as well, there's the wildcard, which says, if you can't handle those other three formats, just send me anything, I don't care. And again, all this doesn't really matter because the web server is just going to do what the web server is going to do, and the client's going to do what the client's going to do. This one was new to me. I never seen this before, but this is just browser security stuff. We're seeing more and more of this just in the spectrum of things. Say privacy and fingerprinting, all that is, there's all this signature stuff between your server and your client. So there's data in the slides if you want to go back and read it. I did some research on it. We also have accepting coding, and I like this one because this is how we make our server a little bit more efficient. Accepting coding basically says, how do we want to compress or send this back to the client? And by default, there's a couple different ways. There's deflate, there's gzip, Bertolli, and zstandard. Zstandard I had never heard of before until doing research for this talk. It didn't exist last time I did heavy work on web servers. But gzip is what we used to use all the time. Deflate, works on everything, but so does gzip now. And gzip just works better. It's better compression, and it's much faster. Bertolli works really well as well. It's also pretty widely supported. I don't know off the top of my head anything that doesn't support it. Zstandard, I'm not sure about support across the board, but I just know it's super fast, and it's the type of thing that you can tune. So if your server's really working, has high CPU, you can dumb down the compression just to make it more performant over time. And these come in as another set of, another set of headers, and they're in no particular order. It's just saying these are the things that I accept: gzip, deflate, Bertolli, or zstandard. I have a demo of taking the exact same code, and I implement compression. So it's primarily the same request, but I have a little check in here that says, all right, if there's a header for accepting coding, that probably means that the request wants to do compression. So let's do a test. And we go read the accepting coding header, and it splits it up by comma to figure out, all right, how many types do you care about? And we just select whichever one's first. That's my implementation. And I also had a comment here. I should uncomment. There we go. Now, I could have a web server that doesn't support Bertolli. So even if the request says, I can do it, I want you to handle this, I don't have to handle it. I can still send it back as gzip. So I can pick my compression, and then in my handler, in my response builder, it's in the handler. So I still build the message the same way I would before. That part doesn't change. But as I send back the request, I tell it, well, compression was requested. I'm going to go compress the data. I am cheating here. I'm using the framework to do gzip, Bertolli, or deflate for me. It's built into the framework. So do one of the three, or do no compression at all. And I'm going to send back the compressed stream. The important part is I have to tell the response, I'm sending back compressed data. So please make sure you're processing it correctly. And again, I have to send back the content length, even though it should be much smaller now in the long run. And everything else is primarily the same. If I run this without any breakpoints, let's do a zoom. Let's see if this actually works. So this first request, I didn't actually test this part before the demo. So So let's make sure this all works. Okay, so this came in at 6 kilobytes. Okay, so if I refresh, scroll down, localhost, they came in at 2 kilobytes. So yeah, compression worked really well in this case. And we can see in our response headers that I told it I'm sending back gzip encoding. The DevTools does all the decompression for you. But there's all my data in one response. Now, we could also play with this inside of Postman. So let's see. I did the request before that had no compression, and that was 6.6 kilobytes. Let me hit send. All right, this isn't showing me the compressed value, which I actually don't know how to get in Postman because I'm telling it to do. Let me do gzip. Maybe it totally just sucks. Hit send. Nope, yep, 2.69. So I might have a misunderstanding of how Bertolli is supposed to work because it doesn't seem any better than just regular, no encoding. Because if I do regular no encoding, I broke it. I broke it or something's caching. I don't know. It's too late in the day for me to care. But that's just basic compression. Other things to talk about. If I had infinite time, which thank goodness I don't, for all of our sakes, what do we do next? Well, this web server I built is terribly inefficient. Like I would never put this in production. It's really good for a demo and kind of demonstrating the points. But where do we go to next? Well, let's go back to the request response cycle. When I make a request and I wait for a response, no more requests can come in until that first request is handled and responded to, or it errors out. What happens if my request takes a much longer amount of time than I anticipated? No other requests can come in. They're all held. The socket has what's called a backlog. So there's requests that will sit there ready to connect as soon as I'm able to connect on them. But if I'm off doing something else, I can never accept those connections. And that backlog is finite. I have it set to 10, but you can make it 100 or 1,000. A lot of it's dependent on RAM. But if a socket tries to connect and there's no connections available in the backlog, your client's just going to throw an error that it can't make the connection, which is never good. So what if we could take our server and we can make it multi-threaded? That's the next big iteration. Is I should be able to handle multiple requests and responses at multiple times across multiple threads. That's the next thing I would do if I was building a bigger demo. And the reason I'm not doing it here is that it's incredibly complicated and the talk is simple. It's also more likely to crash because I'm the one writing it. That's not the point. So we want to handle multiple requests and multiple responses across multiple threads. And doing that, we would have crazy good performance just in a simple web server. And all modern web servers do this now anyways. So it's not like, I don't think there's a single threaded web server out there that's super performant. The other thing we would want to handle is this particular header, the keep alive, so connection keep alive. And I really tried to set up a demo of showing this off. I wasn't able to make it work though in the time frame. But what keep alive does is when you have a client that makes a request to a server, there's a bit of overhead in just making that initial connection. So what if we could use one connection for multiple requests? Let's go get my HTML. Let's get my JavaScript or CSS. Let's just use that one socket without having to open multiple sockets. That's a general idea with keep alive. I could create a request, send back responses, request response, all inside of a single socket and not having to continuously open and close sockets. All right. And the other thing that if we were looking at implementing a more modern web server is some sort of caching. And we see this nowadays and we take it kind of for granted, or we curse it. Who curses caching sometimes? Yeah, yep. This is safe space. So in our headers, our client will tell us what kind of caching it's expecting. It will say, all right, here's what I'm expecting for a cache. If it already has something cached locally, it might send like an E tag saying, this is something I already know about. Has it changed? And we can go off and we can say, yeah, what you have is already good on your disk. You should just use what's inside of your cache. Or we could say, well, your resource has changed. Here's a new version of the resource. We can invalidate the cache. A lot of that comes back in the response. So here's a sample of response where I'm saying the last modified date. So this content was last modified on a certain day, a certain time. Here's an E tag for it, a way to identify or hash the content. The client can just send me that information, and I can give it a thumbs up or thumbs down. This is really useful just for building more high-performant web servers, because you don't want to have to go to disk every time. You don't want to send your request to a processor every time. It's just little things that we can do. But I'm going to go ahead and open up for some questions. That's enough of my silly demos. Or you could all just go get drunk before the movie. That's fine too. But I mean, thank you all for hanging out with me. I know it's the last session. Everyone's exhausted. These chairs are incredibly comfortable and easy to fall asleep. So if you're asleep right now, wake up. But I'll also stick around. I'm here all evening. And don't ask me questions during the movie, though. That's rude. But thank you all for hanging out with me. No. What's up, Jeremy? Oh, absolutely. I always had an appreciation for it. One thing, so you and I are both in the .NET space. Like, we know what's going on there. And when so anyone who's not in .NET, they introduced a thing a while back called span. And the big thing that span does inside of .NET is it lets you access memory is like dynamically. So you could say, I want to take a chunk of memory, I want to be able to read it. And it's safe. You won't accidentally corrupt anything. And this is incredibly useful for web servers because you could take a block of memory and not have to allocate strings to read different portions of it. Like if you look at my code, it is super allocation heavy. I'm looking at this little string and then that little string and so on and so on. Like they've added platform features or language features, so they don't have to do that. They could look at an entire HTTP request without having to allocate any additional strings. Or what does David Fowler like call it? Like zero allocation string reading. Yeah, yep. So like the amount of engineering that has gone in to make that part simpler, I wish I was that smart. It's crazy the things that they're doing. And I would love to take this little demo and like rebuild it with span and try to hit that goal of, all right, let's not allocate as much memory as Kevin is. Because this is the stuff that makes .NET crazy fast. And I know if you're out there going, why is he talking about .NET? And like, yeah, it's just awesome. Shut up. But yeah, I have a great appreciation for the work they've done. But it's like I'm talking about the .NET team, but Apache was doing this years and years ago. Like they were the forerunner, and they were solving all these problems. You have Nginx that does this really well as well. And then anything that sits between a client and a web server, like some sort of proxy, like load balancing systems, they have to care about all this as well, because they have to basically take your message, process it, and not screw anything up. Again, it's amazing any of this works, like as complicated as it is.
That's even before you get into SSL.
Oh, so exactly why I didn't cover anything above HTTP 1.1. Like I didn't want to have to do SSL negotiation as part of the talk. That would be a whole nother set of to-dos. So again, yeah, don't use my code in production at all. Which, funny enough, so just what I remember from .NET history. So .NET created its own web server called Kestrel. And there was a time where they were specifically telling us in the community, like, don't use Kestrel directly from the internet because it didn't have SSL built into it. It just had basic web server functionality. You were supposed to use it behind something. And of course, a lot of people just went, what? No, I'm just going to expose it to the internet, which was a bad idea. But eventually, it became a more mature platform to use. All right, everyone's quiet. Well, thank you all so much.